So in this lecture, we are going to discuss chapter number 8 of your textbook, which is related to the fundamentals of GPIOs. In this particular chapter, we are going to discuss the introduction of GPIOs, which we discussed in the last lecture as well. We will discuss some salient features of the GPIOs of the board which we are going to use, and then we will discuss how to configure a single pin or a parallel port or a set of pins onto a microcontroller. What will be the steps to configure, and then we will discuss a few examples on which we will interface a few pins as either inputs or as an outputs, and then we will try to trigger an LED. We will try to interface a switch, or we will try to assemble some 7 segments or some LEDs or some LCDs. So these will be the examples that we'll be discussing in this lecture after discussing the configuration steps. In the previous lecture, we started with the introduction of GPIOs. That GPIO, general purpose input output, is basically a physical pin that is embedded onto a microcontroller and which can be configured through software to become either digital input or digital output or even analog input. In that case, in terms of digital domain, you will set the voltage levels of the pin and you will make it on or off based on the level of voltage at which the pin is configured. And if the GPIO is configured as an input, then the software will only read the value of that pin via the voltage levels, and that will be set by the program or the sensor at which that pin is connected to. So if it is input, then you can only read that particular GPIO. If that is output, then you can set its state either on or off state through a software. And same register will be used for either read operation as well as for the write operation. So we will see in a little while, there will be only one register called GPIO data register, and through that data register you can read the value of any input or you can write the value of any input or of to any output. Then we discuss the pull up pull down configurations as well. This was the basic diagram of simple block diagram of a GPIO pin. It had two flip-flops, one for read operation, one for write operation. If you want to write something, you will trigger this flip-flop. Whatever data that bus will be giving you, that will be transferred through this D flip-flop onto this buffer, and this buffer will set the state of this NMOS transistor. And similarly, if you want to read something, then whatever data this GPIO pin is currently giving you, that will be passed through that buffer, that will be passed through this flip-flop onto the bus, and processor will read that data through the bus by applying some control parameters and some sort of address to this particular bus location. This was a more comprehensive diagram in which there were some driver logics as well. There were some slew rate slew rate modules as well, and there were some Schmidt triggers that will be triggering and that will be used to drive this D flip flop. These were a few features of them. The TM4C123 microcontroller that we are going to use in your lab sessions as well, that has 80 megahertz clock frequency, maximum of 80 megahertz clock frequency, but it can be configured to any other lower frequency range as well. It has a built-in FPU in it. It has a SysTick timer, which has a capacity of 24 bits, and it will be used to generate the time-based generations. And it has a JTAG cable. It has a SWD, which is serial wire debugger, and it will be used to debug or program your code. JTAG cable will be used to program your code. SWD will be used to debug your program. It has a built-in NVIC installed in it. NVIC is nested vector interrupt control, and this controller will be controlling the interrupts in handler mode. And whenever the interrupt will come, it will have its own priority. So you can adjust 8 different priority levels, and the NVIC will tackle those interrupts based on the priority level of those interrupts. And there are a total of 7 system exceptions that NVIC can manage, and there are 65 peripheral devices which can be linked with TM4C123, and each of those peripheral will generate its own interrupt. So there are 65 different peripheral interrupt support, and there are 7 system exceptions which has the support in NVIC. So NVIC can easily handle 7 system exceptions, and 65 peripheral interrupts. What are those interrupts? Those will be discussed in chapter number 9, maybe in the next lecture, hopefully. It has a total 64 pin package. This is the diagram of it. This is the diagram of that TIVA 4C. It has a total of 64 pins. Out of those 64, only few of them are hardware embedded, and rest of them are basically the internal pins, which are connecting different peripheral devices with each other. So there are a total of 64 pins. Those 43 pins can behave as a GPIO. So you have the flexibility of using 43 different pins simultaneously, and those GPIOs have been divided into 6 different ports. Each port has been given a label. For example, port A, port B, port C, up to port F. Starting from port A to port D, these 4 ports have 8 pins in them. So port A has different 8 pins, which is PA0 to PA7. PB0 to PB7 are the port B 8 pins. Similarly, port C has different 8 pins, and port D has different 8 pins starting from PD0 to PD7. PE, which is port E, has 6 pins, and port F is the smallest of them. It has only 5 pins in it. So port F will have the flexibility of 5 pins, port E 6, and rest of them have 8 pins. All of these pins can be configured as IO, but some of them also have some special peripheral attached to it. And those special peripherals can be multiplexed along with that GPIO functionality. That pin can be used as a specialist pin or alternate functionality pin. So you can configure a single pin as an alternate functionality pin as well. 13 pins out of those 64 pins are used for the power supply modules. So VDD and grounds are attached at 13 different pins. 4 are reserved for the external clock sources, and rest of them for the reset, wake up, hibernation, and external battery connection pins. Then each GPIO has its own pull-up, pull-down configurations. Each of them has its own current sourcing capability. A few of them has a current sourcing capability of 2 milliampere. It can only drive a sensor which has a current rating of 2 milliampere. A few of them has a current sourcing ability of 4 milliampere. Few 8 milliamperes, while there are 4 GPIO pins located at locations which can be configured as an input, and if being configured as an input, they can sync up to 18 milliamperes current. So this is the maximum capability of current sync ability of TIVA board. You have a slew rate control that is capable of providing 8 milliampere output drive. Each port can be configured as an open drain pin or as a pull up or pull down pin, and some of the port are capable of tolerating 5 volts as well. So the TIVA board actually operates on 3.3 volt, but a few of the pins are the one which can tolerate up to 5 volts as well. The minimum connectivity for a TIVA pin is to have a DC power in it, embedded in it, a clock source that will be generating the ticks, the reset pin that will have the capability to reset the hardware, and JTAG pin to burn a code onto the microcontroller, and a serial wire debugger to debug your code or to connect any debug interface to it. This is a simple diagram, a VCC, a few power supply pins, a few hibernation and wake up pins. This is the JTAG interface. This JTAG interface will be used to burn the code or to debug the code. These are the oscillators. These oscillators are providing the clock to your microcontroller. This is your reset pin. Reset pin will reset the whole architecture for you. And this is the ground pin. So this is analog ground as well as digital ground. These are the oscillators that are providing the clock source. This is the JTAG cable, the VCC source, and the reset pin. This is the minimum connections which are required to trigger or use a TM4C controller. And this is a complete of them. This is the debug section of it. It will have its own JTAG cable. This is a JTAG cable or a debug connector. It has this debug system. This debug section has its own debug connectivity. These are the expansion headers or the pins of the GPIO. This is the actual microcontroller. This is its flash memory on which the code will be burned. This is the microcontroller of it. It will have its own registers in it. Then this is another external header. This is an LED which will be configured in a little while shortly. These are the two switches. So these two switches can be connected to two different GPIOs and can be used as an either interrupt generator or can be used for any other purposes. And this is the reset button. So this is the reset button. Reset is written over it. This is the flash memory via flash chip. This is the microcontroller. The two different expansion headers which can be used to connect any external device or any other peripheral to this microcontroller. Two different switches which can be used as an interrupt generator. One RGB LED. So this is a complete module or complete hardware board of your TM4Z123. And this is a summary of it. Starting from the configuration steps, this is where we left the last time. So starting from the configuration, a GPIO can be configured if you will configure four different steps. The first step is to configure the clock and bus of it. Then you will control its data, whether its direction would be output or input. You will select its mode and you will select its pad. So these four configurations are very
सीमी सर
important to configure. Ji.
सर इसमें RxTx पिन होती है जिससे ऑडियो में होती है
RxTx पिन PA1 है ना, यहाँ पर नजर नहीं आएंगी, वो इस JTAG के अंदर ही होती हैं. ये जो आपका USB डिबगर कनेक्टर है ना, इसके अंदर ही वो दो पिन होती हैं RxTx वाली भी UART 0 के लिए. हमारे पास असल में एक UART नहीं है, आर्डिनो में एक ही होता है बस. हमारे पास यहाँ एक नहीं है, यहाँ पर 5 या 6 हैं. तो जो UART 0 है ना हमारे पास, उस UART 0 की TX RX पिन इसके अंदर ही एम्बेड है. तो UART 0 को आप यूज कर सकते हैं एज अ सीरियल मॉनिटर. बाकी जो UARTs हैं वो उनकी कनेक्टिविटी इन पिन्स के साथ है. Okay, first comes the clock configuration. First of all, if you will, this is the complete flow chart of controlling a single pin. In the very first step, we will try to enable the clock for the port. First of all, pins are connected with the ports. So you have to enable the clock for the port. Unlike Arduino, in Arduino, everything will be turned on once you will connect it. But in case of Tiva, everything will be in hibernate mode or in sleep mode unless you provide clock to that. So it's the first and very basic step, and the very first important step is to provide the clock to that peripheral. So first of all, if you want to configure any particular pin, you are supposed to turn on the clock for that port. So the very first step would be to turn on the clock. Then in the next step, you will choose whether you want to use the alternate functionality or you want to use it as a GPIO. If you want to use the alternate functionality of it, then there will be a special register. That register will be shown in a little while. In that register, you will put something, some 1 or some 0 in a specific bit to turn on the alternate functionality of that pin. If the alternate functionality will be enabled, you will simply go to the port control directly. In your port control, you will select for which alternate functionality you want to use that specific pin. That specific pin can be connected to some sort of UART or some sort of SPI or I2C or timer. The port control register will be choosing among one of those multiplex devices through which that pin will be used as an alternate functionality. So if you have turned on the alternate functionality, the next step would be to control the port or to control the peripheral at which that pin will get multiplexed. So if something in your port control register, after that, one of those devices will be multiplexed to that pin, and that pin will start behaving, let's suppose, as UART transmitter or UART receiver or maybe timer PWM generator. So this is the way of configuring a single pin as a alternate functionality. If you will not use the alternate functionality, in that case, if this check is false, the next check is if you want to enable it as a digital pin. If you want to enable it as a digital pin, there will be another register. That register is called digital enable register, DEN register. That DEN register will be accessed and will be given some value that will decide whether you want to use that pin as a digital pin or you want to use that pin as a tri-state pin. If you will put 0 inside that register, sorry, in that case, your pin will simply go to the tri-state mode. Tri-state mode means that will be high impedance state, true state, or false state. If you want to use it as a digital pin, then you will put 1 in that registered bit, and after that you will take another decision. And that decision is if you want to use the pin as an input or as an output. You will select the direction of it. Direction means if it will be selected as an output, then data will be driven from processor to the pin. And if that pin will be given as input control, then in that case data will be driven from pin towards a processor. So this direction register will set whether the pin will behave as an output or as an input. If you want to behave the pin as an output, then in that case there will be last possible setting, which will be pad control setting. And in the pad control setting there will be another register once again that will decide whether you want to use that pin as a current drive pin, as an open drain pin, or as a slew rate pin. So you will select the slew rate of that, you will select the open drive configuration or the current drive configuration of that pin. If that pin will be given output control. If that pin will be given an input control, in that case you will set the pull up configuration or pull down configuration for that pin. So this is the complete flow chart or flow hierarchy of configuring a single pin. There will be a register for this purpose to enable or disable the clock. There will be a register for this purpose to select the alternate functionality. There will be a specific register for this purpose as well to make it digitally enabled. There will be a special register to control the direction of a pin. And there will be a very few registers. Those will be controlling the pad control settings, whether as an input or as an output mode. And there will be a port control register as well. So there are a few GPIO registers: a port control register, the pad control register, direction register, digital enable register, alternate functionality register. These registers are the most important of them to configure a single GPIO pin. So this was the abstract flow chart. Now let's discuss the modes and let's discuss the registers of it. The very first register is called the GPIO RCGC register. RCGC register is the one that will be controlling the clock to GPIOs. So RCGC register is a special register. It is memory mapped and it has this address. How this address is being calculated? This calculated using the data sheet. Just give me a second. I will open the data sheet for you.
सर टीवा बोर्ड का जो इंटरनल क्लॉक यूज करता है चिप के अंदर या एक्सटर्नल क्लॉक होता है?
नहीं, इंटरनल क्लॉक होता है इसका। टीवा के अंदर इंटरनल क्लॉक है, वो उसके मल्टीपल सोर्सेज हैं। तो वो सोर्सेज के बारे में हम डिस्कस करेंगे जब हम टाइमर स्टार्ट करेंगे। तो टाइमर से हम इसके क्लॉक सोर्सेज देखेंगे।
वो जो एसपीआई वाले होते हैं मॉसी और वो वगैरह मास्टर स्लेव क्लॉक वाले।
नहीं वो डिफरेंट चीज़ है। जो एसपीआई मॉड्यूल है ना, उसमें वैसे तो वो सिंक्रोनसली सिस्टम क्लॉक पे ही चलते हैं, लेकिन वो क्लॉक की डिस्कशन डिफरेंट है। वो जब हम एसपीआई स्टार्ट करेंगे ना, फिर उस प्रोटोकॉल को अंडरस्टैंड करेंगे। वैसे वो है सिंक्रोनाइज्ड, वो सिस्टम इंटरनल क्लॉक पे ही चलता है, लेकिन वो एक्सटर्नल क्लॉक के साथ भी कॉन्फ़िगर हो सकता है एसपीआई। लेकिन जो अभी जीपीआईओ कॉन्फ़िगरेशन है वो सारी इंटरनल क्लॉक पे हो रही हैं। Okay, for every microcontroller that you will use in your rest of your life, that microcontroller will always have its own reference manual or called data sheet. For example, the microcontroller that we are going to use is LM4F120H5QR. This is the old name of this microcontroller. The new name is TM4C123. So this is its data sheet. This data sheet will be uploaded on the Piazza page as well. Within this data sheet, there are multiple sections of it. Just give me a... These are the sections of it. You have complete architectural overview, you have complete processors, block diagrams, the register maps, and everything related to it. So these are the register maps of it. The first preliminary registers, Cortex M4 registers. In fact, let's go to the main section first. is chapter 10, GPIOs. This whole chapter has been taken from this particular section. So these are the concepts of GPIOs, 43 pins, which have been divided into these ports. These are the functionality of each pin. PA0 can behave as a UART0 receiver as well. PA1 can behave as a UART0 transmitter. PA2 may behave as an SSI clock as well. UART1 receiver is connected to PB0. UART1 transmitter is connected to PB1. So these are the alternate functionality charts. A few of the pins can have only one multiplexed alternate functionality. Few of them has two or more alternate functionalities as well. For example, PB0 has a multiplexed UART1 receiver as well as timer 2 compare pin. So this can behave as a timer 2 compare pin, or it can behave as a UART2 receiver as well, apart from its GPIO functionality. If you want to use it as a GPIO, you can configure it in that way as well. If you want to configure it as an alternate functionality, then the possible alternate functions for this particular pin is it may behave as either UART1 receiver, or it may behave as compare value. So this is a whole chart of each and every pin. And this is where the register maps lies. These are the few registers that can be used to configure a single GPIO. There is a GPIO data register, direction register, interrupt sense register, which will be discussed in chapter number 9, interrupt both event register, interrupt event register, interrupt mask register. These are the registers related to interrupts. This is the direction ho gaya. This is the direction register. This is the alternate functionality selection register, AFSEL. AFSEL stands for alternate functionality selection register. Then there is digital enable register, DEN register, which will be used in a little while. So each and every register will have its own base address, will have its own offset value in it. So we will get an base address for any port. You will add some offset to that base address and you will access that particular register. And after accessing that register, you may either write that register or you may even read the value from that register. So this is same as that of assembly notation, but we'll be using this notation in your C language just for the sake of simplicity. But you will have a base address for each and every port. For example, here the base addresses are also written. GPIO's base port F base address is this one. GPIO port D base address. In fact, this is the range of offsets. We will have the offset values in some table. This is the base values. So port A has a base value 40004000. This is the base value at which the port A's registers are starting. And after adding some offset to this base value, you can select either data register of port A, the alternate functionality register of port A, direction register of port A, or maybe digital enable register of port A. So you will keep on adding the offset to this base address. You will keep on accessing the registers of port A. Similarly, the base address of port B is 40005000. So you will fetch this address, you will add a few offset in it, and you will start getting the registers of port F. Similarly, port C also has its own base address, port D, port E, and port F. Every port will have its own base address assigned to it. And after adding these offsets, which are given in this table, after adding these offset to it, you can access each and every register of that particular port. So all this information lies in your datasheet. So reading the datasheet is very important because datasheet will have the base addresses, it will have its offset value, it will have its registered map as well. Registered map will simply tell you which bit will do which thing. So each and every bit has its own functionality. So while configuring a pin, you are supposed to know the base address of the port. Then you are supposed to know the offset value of it. So by adding offset to that, you can access that register. And after accessing that register, each and every bit will tell you some meaning of it. So every bit has its own meaning. If you want to do something, you have to put something in that particular bit. So each bit will have its own meaning, and that meaning will be told by the register map of it. So this is the register map of it. Data registers, register map. This is the register map of direction register. Similarly, every register has its own particular map assigned to it. So every bit of every register will have its own particular meaning. So if you want to enable the clock, you will access this particular register, RCGC GPIO register. RCGC GPIO register is a special register which is memory mapped to this address. So if you will use this address, you can access this register. And inside that register, each and every bit of it is assigned to each and every port. For example, bit 0 is port A. If you will put 0 inside bit 0, you are disabling port A. If you are putting 1 inside the bit number 0, then in that case you are enabling the clock for port A. So if you want to enable the clock for port A, you are supposed to put 1 inside bit 0 of that register. Bit 1 is mapped onto port B, bit 2 is mapped onto port C, and keep on going onwards. Bit 5 is mapped onto port F. So if you want to enable any particular port, you are supposed to put 1 to that relevant bit of that corresponding RCGC register. And after enabling that, you are supposed to wait 3 clock cycles to write after writing something into RCGC register. So you are supposed to wait for 3 clock
Excuse me, sir.
cycles. जी.
सर मैं क्लॉक साइकिल्स के लिए 3 क्लॉक साइकिल्स के लिए वेट क्यों करना पड़ता है? क्लॉक्स तो
ये
सिंक्रोनाइज नहीं है?
अभी पता लग जाएगा. ये 3 क्लॉक साइकिल्स में वेट क्यों करना पड़ रहा है, ये भी आपको पता लग जाएगा आगे जाके. Then configuration is called bus configuration. In the bus configuration, you have specific registers associated for each port, as you have seen in the data sheet as well. Inside your data sheet, you have seen that each and every port has its own set of registers, which can be accessed through base address. Now, there are 2 different buses inside the TIVA board that are connecting your microprocessor with your GPIO ports. The first bus is called advanced peripheral bus. The other bus is called advanced high performance bus. The first is called APB. The second is called AHB. If you are using APB to configure your path through processor to your GPIO port, in that case, you are supposed to use the base address of APB. And if you want to configure a GPIO port via AHB bus, in that case, you are supposed to use the base address of AHB. If you go back to the data sheet once again, as you can see over here, or if it will be, as you can see over here, there are 2 different base addresses assigned to every port. If you are using APB bus, then in that case, the base address for port A is this one. This is the base address for port A if you want to configure port A via APB bus. And if you want to use AHB high performance bus, in that case, base address of port A will be looking like this. So this is the base address of port A, GPIO port A, if you are using AHB, and this is the base address of port A if you are using APB. Most of the times, for the general purposes, APB bus address is used. So APB bus is configured most of the times, and the base address for port A in the case of APB will be 40004000. But you can use AHB bus as well. There is AHB bus available in your TIVA board as well, and that has a base address of this one. So there are 2 different base addresses to each port assigned to it because of 2 different buses. All the registers associated with each port is accessible from both of these. Both of these buses will access all the registers which are configured for the port, but they are mapped to different address spaces. Since APB bus has its own offset, its own base addressing, the AHB bus has its own base addressing, so we say they are mapped onto different address spaces in the peripheral address space. For example, if you are using port F registers, so for port F, APB bus will have this offset, will have this base address, and it will keep on you will keep on adding offsets to it. You will keep on accessing the registers of port F. And if you are using AHB bus, in that case, the offset will be this value. You will keep on adding offset to this base value, and you will keep on propagating till this range. So this is the range for port F if you are using AHB. This is the range for port F if you are using APB. So for APP purposes, this is the base address. For AHB purposes, this is the base address. And you will keep on adding the offsets assigned in the data sheet. In this offset, in this base value, you can access each and every register of that particular port. Next comes the mode control configuration. Mode control configuration are done using a special registers. They are accessed. The first one is the GPIO mode register. They are accessed directly by the software. You can select the mode of a GPIO by just putting 1 to the relevant bit. Each bit will be mapped onto a pin. So if you want to configure a single pin as a alternate functionality or as a GPIO mode, you are supposed to put either 1 or 0 to the relevant pin that is connected to specific bit. For example, PA0 is controlled via bit 0 of each of these registers. Similarly, the PA1 will be controlled via bit 1 of all the registers. So each bit inside the port level register is representing each pin at the port. The alternate function, the port pins are controlled by the hardware of alternate functionality module. The corresponding bits of this particular register, GPIO AFSEL register. This is called GPIO, general purpose input output, alternate functionality selection register. This is a special register which can be accessed by adding offset to the base address, which is controlled via software. And if you will put 1 to the relevant bit inside this register, that particular pin will be assigned as an alternate functionality. But if you will put 0 inside it, that pin will behave as a default GPIO. And after configuring the AFSEL register, there is another register called port control register, PCTL register. This PCTL register is called port control register, and this port control register will control the multiplexed peripheral device at which that pin is connected. If you want to configure a pin as a UART, you are supposed to put something inside this port control register to configure or multiplex UART module to that pin. So port control register will be selecting the peripheral multiplex devices. AFSCL will select whether you want to use the pin as a GPIO or as a special purpose. And if you will put 0 inside this register, that pin will be triggered as a default GPIO. If you will put 1 to the relevant bit of this register, that pin will start behaving as an alternate functionality. So this is the purpose of alternate functionality register. This is the purpose of port control register, to select one of the connected multiplexed peripheral functions. Then analog input pin. If you want to configure a pin as an analog input, then in that case, there is another register called AMSEL register. AMSEL stands for analog mode selection register. If you want to configure a pin as an input and you want to connect analog to digital converter ADC to that input pin, then in that case, there is a register called analog mode selection register. That register will be accessed by adding offset to relevant offset in the base address. And in that register, you will put 1 to the relevant bit at which you want to trigger for the pin at which you want to trigger it as an analog input. For example, if you want to trigger or if you want to configure bit pin number 0 of any port, then in that case you will put 1 inside. Sorry. If you want to configure pin 0 of any port, then in that case you are supposed to put 1 inside bit 0 of this register. So bit 0 is mapped onto pin 0, bit 1 is mapped onto pin 1, and you will keep on going onwards. Bit 7 will represent the pin 7 of it. Okay, then pad control settings. These pad control settings will be covered in a little while. The basics of them are the GPIO direction registers and GPIO DEN register. In order to use pin as a digital input or as a digital output, first of all, if you want to trigger as input analog input, then in that case, once you will select AMSCL register, DEN register will get nullified. But if you will put 0 inside SCL register, it means you are not in a position to use that pin as an input pin. Then in that, sorry, analog pin, then in that case, you will use that pin as a digital pin. And if you want to trigger a pin as a digital pin, you will access this register, DEN register, called digital enable register. Register map is same as that of AMSCL. The each bit will represent each pin of a GP of that port. Bit 0 will represent pin 0, bit 1 will represent pin 1, and keep on propagating onwards. You will select the pin 7 via just setting or resetting bit 7 of that register. So if you will set the pin in the digital enable register, that particular pin will start behaving as a digital input, digital pin. So this is called digital selection pin or digital enable register. This is the complete chart of it. Once again, if you will revise it, this function will be done by RCGC GPIO register. If you have an RCGC GPIO register, in that register, each bit is representing each port. If you want to turn on the clock for particular port, then that bit will be set to 1. Then alternate functionality, it will be done using AFSEL register called alternate register. If you will put 0 inside it, that pin will be as a default GPIO. If you will put 1 to the relevant bit of it, then that pin will start behaving as an alternate functionality. And that alternate functionality will be chosen by PCTL register called port control register. That will be selecting the port control. Then the digital enable version, DEN register, is a special register that is used to switch your input pin, any GPIO pin as your digital pin. And then there is a direction register called DIR register, and that DIR register will control the direction of that particular GPIO. Okay, next aspect. Pairing a data direction bit in the GPIO DIR register configures the GPIO pin as an input. There is a special register called DIR register, direction register, and each bit of this direction register is again representing each pin of a GPIO of that port. So if you will put 0 inside that relevant bit, then it means that pin is assigned as an input functionality. And if you will assign it as an input, then in that case, value on that GPIO port pin will be stored in the corresponding bit of the GPIO data register. There is another register called GPIO data register, and this data register will store the data coming from some sensor to that pin. And if you will read this data register, you can access the data that is coming from some sensor. And if you will set a data pin, set direction pin means you will put 1 inside it. So if you will put 1 inside the relevant bit of GPIO direction register, it will configure that GPIO port pin as an output pin. In that case, you will write the data register. The same register will be used for input purposes as well as for output purposes. In this case, your data register will get writable, and you will write something to this data register, and those corresponding pins will get the updated value. So same data register as well as the same data register can be used as for input purposes as well as for output purposes. Now, there comes a case in which a few of the pins are behaving as an input and a few of the pins are behaving as an output of the same port. In that case, your GPIO data register will write some pins, some data to some pins, and that will read data from some other pins. So in that case, there is a concept of data masking. Now, what is this concept? Let's suppose if you want to change the state of any particular GPIO pin that is configured as an output. Let's suppose you want to turn off or turn on a specific pin that is connected to some output device. Let's suppose an LED. You want to turn off that LED or you want to turn on that LED. You are supposed to do it in three steps. What are those 3 steps? First of all, you will read the data register. If you are reading the data register, you are reading the content of those pins which are assigned as an input pin. Its value is updated by modifying the value of the desired bit. If you want to update only one pin's data, then you will update only one bit. If you want to update the data of multiple pins, you will update the desired bits, and then you will write back that data register. While doing these 3 things, you are supposed to use three different instructions, and it will take 3 different clock cycles to perform just one write operation. This is the way RCGC register is written. RCGC register is read first, value is updated, then its value is written back. That is why we have to wait 3 clock cycles to perform this execution. This is the answer of the previous question as well. So very highly inefficient way. This inefficient way will consume 3 clock cycles whenever you want to write something onto some pin. This inefficiency has been taken care by data register masking concept. This concept is adopted only by TIVA. This is adopted only by Texas Instruments. And this concept is called the register masking because in this particular domain, we can mask the data register as well. To improve the software execution, the GPIO ports on TM4C123 allow access to individual bits in the GPIO data register. You can access even a corresponding individual bit inside the data register. How can you do that? You can adjust the offset to the data register by masking or unmasking each and every bit. Let's look at an example of it. Let's suppose this was my data register's initial address or base address. This is the base address which is written in the form of a macro. So this macro is representing the base address, which is 0A4 in terms of hexa. Sorry, no, this is not 0A4. You have added an offset 0A4 to it. This was the default database address. This is the offset that you have written inside it, 0A4. If you will write 0A4 over here, 0A4 will be written in the address column. This 0A4 will look like this. 0010, this is 4, 0100. Starting from bit 0, this is my bit 0. So starting from bit 0, this is 0100, which is 4. Then A means 10. 10 means 1010. So 1010 is over here. And 00, which is the last one, is written over here. This offset has been added in the base address of data register. So data register's base address has get updated to this particular value. Now in this particular scheme, you want to write the data 101000101 inside your data register. But only those bits will get written at which the address is representing 1. If the address bit is representing 1, only in that case data will be driven from your buffer to your data register. Otherwise, your data will get masked. So in the case, if your address bit at that particular location is 0, that particular value will not be passed through the buffer and that will not update your data register. So this bit has been masked due to the address offset inside the data register. So just by adding a limited offset in your data register, you can easily mask or mask a single bit inside your data register. So X will represent that the previous value will remain intact. There will be no update because you have masked that particular bit by adding relevant offset inside the base address. Now let's look at the case. Let's suppose if I want to only update the 4th bit. I only want to update the 4th bit. That 4th bit has been configured as an output and rest of all the pins have been configured as an input for that particular port. I am only interested in updating this particular bit. In that case, I will put 1 over here, I put 0 everywhere else, I will compute the hexadecimal value, and that hexadecimal value will be added in the offset of data register. And this is how I can only unmask one bit of data register, and I can mask the rest of the bits. So this is the way called register masking. For that register masking, you can update your GPIO data registers bits on your according to your own choice. Is this concept clear? क्या किसी को रजिस्टर मैस्किंग में कोई इशू है? क्या सबको मेरी आवाज आ रही है?
यस सर।
जी, ये कॉन्सेप्ट समझ आ गया सबको रजिस्टर मैस्किंग का? कि रजिस्टर मैस्किंग का कॉन्सेप्ट इंपॉर्टेंट है इन अ सेंस कि ये बहुत ज़्यादा हेल्पफुल होगा अगर आपने एक पोर्ट की कुछ पिंस को एज एन इनपुट और कुछ पिंस को एज एन आउटपुट एक्सेस करना हो। जिनको आपने एज एन आउटपुट एक्सेस करना होगा उसको अलग से मैस्क करेंगे, और जिनको एज एन इनपुट एक्सेस करना होगा उनको अलग से मैस्किंग करेंगे उनकी। This is the complete table of it. If you will put 0 offset, then no bit will be accessible. Every bit of the address unit will be 0 and every bit will be masked. So that is why you will not be able to access the data register at all. If you will add 4 inside it, then by adding 4 inside, you can easily see 1 will be over here, 0, 1, 0, 0, this is 4. The rest of the bits will be 0. In that case, only bit 0 will be accessible. All other bits will be irrelevant or will be masked. Similarly, if you will put 8, in that case, bit 1 will be accessible. If you will put C inside the address, in that case, bit 0 and bit 1 will be accessible. And if you want to access all the bits, if you want to access all these bits, in that case, you have to put 1 from this location till this location everywhere. So the offset value that will come out to be 1, 1, 0, 0. This is C. 0, 1, 1, 0, 0. This is C. Then 1, 1. This is F. So F will be triggered over here. And 1, 1. This is 3. So if you will add F, C inside your base address, then in that case, all the bits will be unmasked. And if you want to mask a few certain bits, in that case, you will put some offset to this address register in this address column, and only those bits will get unmasked. So 3FC is the offset to access all the bits of the data register. So starting from 0, all zeros to 3FC, you can set any offset value, and accordingly you can mask or unmask any combination of these bits which you want to read or write. This is the same example on the read operation as well. This is the data register. You have added an offset value of 18C inside your data register address. So data register's address has been updated by an offset 18C. So 18C will look like 1100 is C over here. Then 8 means 1000. This 1000 is 8, and 1 means 01. So 018C. This is the offset that you have added in the first 10 bits of your address location of GPIO data register. The corresponding bit at which 1 is written, that bit will be masked. That bit will be unmasked. The corresponding address bit at which 0 is written, that bit will be masked. In that case, let's suppose GPIO data register is 10101101. In that case, if the processor wants to read that data register, he can read this bit because this address value is 1. He can read this bit because this value is 1. The processor cannot read this particular bit because this processor address bit is 0. So this bit will get masked. Similarly, this bit will also get masked. This will also get masked. This is 1 over here, so it will be clear for reading. it will also be clear and it will be masked again. So this is a way you can access or you can read only limited bits of the data register, or you can write limited bits in the data register as well. So just by adding this concept of register masking, this register masking address has been added only in the TIVA board. So this register masking address will be used in your TIVA C board to configure or to read or write any particular combination of data by in a single clock cycle. So reading operation or writing operation will be performed only via a single clock cycle. So this is the repetition of previous thing, and this is the whole summary of it. These are the registers that are used to access the to configure a single pin. There is an AFSCL register, alternate function selection register. There is AMSCL register, analog mode selection register. There is port control register. All these three registers are called mode control register. That will be selecting the mode of a register, if that pin will behave as a GPIO or not, if that pin will behave as an input analog pin or as or as a digital pin. And port control register will select the module or peripheral that is currently that is assigned to that particular pin. Then pad control configuration can be done using these registers. DR2 register will select the pin as a 2 milliampere current driver. DR4 register will select that particular pin as a 4 milliampere current driver. DR8 is used for 8 milliampere current driver. If you want to put a pin as an open drain, then OD register is used for the open drain purposes. Pull up register configuration can be done using PU register. Pull down configuration register is used to select the pull down configuration. SL for the slew rate, and DEN for the digital enable register. Similarly, the data control will be controlled by data register as well as the direction register. So these two registers are called the data control register. The offset to the data register is starting from all zeros to 3FC based on the bits that you want to mask or unmask. So this is a range of offsets to the data register. This is the offset for the direction register. These are the offsets for all these registers. And offsets to the base address of that port value, you can easily access these registers, and each bit of these registers will be representing each pin of that port. Any question in the configurations part? किसी को configuration में कोई प्रॉब्लम हो?
सर डिफॉल्ट क्लॉक वैल्यू क्या होती है?
क्या डिफॉल्ट वैल्यू किसकी पूछ रहे हैं?
सर जैसे अगर हमने क्लॉक वैल्यू सेट करनी है, फर्ज करें 16 मेगाहर्ट्ज, तो कैसा करेंगे?
जी, क्लॉक वैल्यू होती है ना, वो 16 मेगाहर्ट्ज होती है। अगर आपने उसको चेंज करना होता है ना, तो हम लोग ये टाइमर्स के चैप्टर में देखेंगे कि क्लॉक मोड्स कौन कौन सी हैं। हमारे पास 4 डिफरेंट क्लॉक मोड्स होते हैं। हम लोग PLL यूज कर सकते हैं, PLL मल्टीप्लायर यूज कर सकते हैं, इसके इंटरनल ऑसिलेटर्स हैं वो यूज कर सकते हैं, या अपना कोई एक्सटर्नल ऑसिलेटर भी कनेक्ट कर सकते हैं। तो उसके लिए हमारे पास वो RCGC जो अभी मैंने मॉड्यूल आपको बताया ना, ये RCGC रजिस्टर्स के और भी बहुत सारे रजिस्टर्स हैं। वो RCGC में जाके हम लोग कॉन्फ़िगरेशंस करते हैं उसके रजिस्टर्स। अगर मैं यहाँ डेटा शीट से दिखा दूँ, डेटा शीट में अगर हम वापस जाएं, RCGC वाला चैप्टर कौन सा है? 4 या 5 है? RCGC जस्ट गिव मी अ सेकंड, मैं ढूंढ लूँ पहले RCGC रजिस्टर्स हैं कहाँ पे। ये कुछ रजिस्टर्स हैं जिससे कि हम लोग RCGC की क्लॉक को एडजस्ट कर सकते हैं। देखिए जब हम टाइमर्स पढ़ेंगे ना, टाइमर्स में मैं आपको बता दूंगा ये रजिस्टर्स। इसमें RC1 और RC2 रजिस्टर्स होते हैं। लेट मी सर्च फॉर इट, बल्कि मैं बता दूंगा जब टाइमर स्टार्ट करेंगे। RC1 RC2 रजिस्टर्स होते हैं जिससे हम क्लॉक फ्रीक्वेंसी को एडजस्ट कर सकते हैं, लेकिन उसमें भी हर क्लॉक फ्रीक्वेंसी हम नहीं रख सकते। हमारे पास डिफरेंट मोड्स होते हैं और उन मोड्स में कुछ मल्टीप्लायर्स होते हैं, बस हम उनके मल्टीपल्स ही फ्रीक्वेंसी में एडजस्ट कर सकते हैं। इसके अलावा और कोई वैल्यू नहीं हम पुट कर सकते। अगर इसके अलावा कोई वैल्यू चाहिए होती है तो फिर हम लोग खुद उसमें जो है ना वो एक्सटर्नली कोई ऑसिलेटर कनेक्ट करते हैं उसके साथ।
सर मैक्सिमम कितना करंट सोर्स कर सकती है एक पिन? हेलो। एक्सक्यूज मी सर। हेलो।
सर आपकी आवाज़ नहीं आ रही।
स्टूडेंट आपको आवाज आ रही है मेरी?
अब आ गई है।
ले
सर आपको आवाज आ रही है?
ओके, कहाँ से आप लोगों को आवाज आनी बंद हो गई थी?
सर काफी देर से बनने
सर
लगी।
जहाँ से हमने एलईडीज का शुरू किया था।
जी, कहाँ से मैंने रिपीट करना है ये? हेलो
सर जहाँ पर माइक्रो कंट्रोलर की डायग्राम बनी हुई थी उसके साथ 3 एलईडी थी वहां से।
क्या यहाँ पर कोई ऐसा है जो मेरी आवाज सुन सकता है?
सर आपको आवाज आ रही है?
हेलो सर।
हेलो सर।
ये किस पॉइंट से मेरी आवाज आनी बंद हुई थी?
सर जहाँ पर एक माइक्रो कंट्रोलर बना हुआ था और साथ 3 एलईडीज थी।
सर नेक्स्ट लेक्चर का टाइम भी हो गया।